This is the final part of our exploration of classes within C++. In this particular one, we're going to have a look at a mixed bag of different content. We'll start off with this keyword, we'll go on to have a look at casting, and then finally we'll finish off by briefly looking at the differences between classes and structs in C++. We'll start off with this keyword. Now, this keyword, you might have used it in Java, you might have used it in C#, you might have used it in C++. So it's a built-in keyword that enables you to refer to this particular instantiation of whatever class it is you're using. So we want to have a little look about, well, why do we have this? And there's a good reason for it. Now, the reason for it ties into how an instance of a particular class gets to be set out and stored in memory. So we've got an example here of, down at the bottom you can see the structure we looked at before, where in terms of the memory is allocated to a program, we'll have a section for storing the code at the beginning, followed by any static data, followed by the heap or free memory in the stack then at the top. And if I have a class called foo, you can see a small example over here, class foo, we're declaring a member variable called dat as an integer, and we've got a method called doWork, which presumably includes some instructions. So if I create a new instance of foo, let's say we've got two here, A and B, they'll be stored in this case on the heap, and we'll go and we'll reserve sufficient memory on the heap to store the data members associated with that particular instantiation. So we've got a couple of hints set aside. Now, the important thing about this is we've got a doWork method. There'll be instructions associated with it, and those instructions will live in memory in the code section. But that does present us with an interesting dilemma, that if I'm executing those instructions in the code section, so here I've got a method called doWork, doesn't take in any parameters, doesn't return anything. How does that method know if it's to deal with A's dat or B's dat? How does it know which chunk of memory it should be accessing in terms of the particular data members it is associated with? So this is an issue of how do we link code in with the particular member variables or data variables for that particular instantiation. And that's where this keyword then comes into it. So the whole purpose of this, it is a semi-hidden argument. Okay, so you access this keyword, but it is an argument, an additional argument that gets put into all of our method calls other than static method calls. So the doWork method, in reality, it actually will have a semi-hidden parameter that will have a pointer to the particular instance of that class that doWork should operate on. So it's always available. We declare a method, as long as it's not static, this additional parameter will be passed in, and it enables then our executable, the code itself, to know which chunk of memory, which data variables of which instance it should be updating. Now, you can access it, you can make use of this. Why would you want to do that? Sometimes you'll see it really for reasons of clarity, that if you have two instances and you copy from one class to the other, you might want to use this just to make explicit to whoever's viewing the code that you are referring to this particular instantiation as opposed to maybe the other class. It's of no use to the compiler because it's implicitly assumed if you use it explicit, or if you don't use it, it will be implicitly assumed. So it's up to you. You can use it explicitly simply by way of greater clarity if you want to within the code. But that's the reason why we need it. That's the reason why in most languages you ought to have a sort of a similar notion to it. So next up, we'll have a look at casting, so transforming data from one type to another. We briefly visited this in one of the earlier talks, and we mentioned that in C++11 there are 4 different types of cast that are defined. And C++98, old style C++, actually had sort of similar semantics to, for example, Java or to C#, though the casting in C++98 was not great because there was no error checking at all. So we want to have a look at how C++11 has tried to improve things. And to be honest, all the things here are sensible, but it's a bit of a mixed bag. There's some things which are not nice, and there's some things which are particularly nice, but we'll have a look at those. start off, I suppose, with something that isn't so nice, and it's called Conscast. So Conscast can be used to cast away the constness of a variable. What does that mean? Here in line 1, we've got a method called foo. It accepts in a character pointer, presumably to an array of data. Fair enough. In line 3, we are declaring a character pointer name and pointing equal to an array of characters, but we declared it to be const. It's read only. So here we're saying that name, points to an array. You can read it, but you can't write to it. It is read only, where we are declaring it as something that should not be changed. That's the reason we put the const keyword in. Line 5, we're trying to call our foo method passing in name, and the compiler won't let that happen. It'll say, we got here a const character name, I'm not allowed to change it. And here you're trying to call a method that just takes in a normal pointer. And a normal pointer you can read to and you can write to. You're allowed to change things. So there the compiler will say, that's not safe. You can't pass a constant, something that shouldn't be changed, into a method that potentially can change it. If you don't like that, in line 6, here we are using the Conscast to basically go to our read-only name and say, let's make you read. We can write you and read and write to you. So in that sense, it gets rid of the read-onlyness, and then we are allowed to pass it into a method that can potentially change it. And that's perfectly okay from a compiled point of view. So Conscast we can use to get rid of anything that is declared to be read-only. Obviously, this is not a sensible or a good thing to do. It's something anytime you see you should be quite wary of. If somebody declares something to be const, it's because they declared it to be const for good reasons in the first place. And there probably is only one instance, or a very small number, but one instance where this can be acceptable is where you're dealing with third-party code. So stuff that you can't change yourself. You have it outside of your bounds or your ability to change it, third-party code. And it has a method, and you know this method will not change the data. So you can be 100% certain this method is not going to change something. In that case, and assuming they didn't declare the method correctly, they just said, okay, even though I won't change things, I want to have access to it so I can potentially change it. So if you know it won't change it, you have some const data, and the method hasn't been declared as accepting const data, then in that case you can get away with using this here simply to interface with a badly defined method. Other than that, should avoid using Conscast in basically any other situation. Next one up then, we have Staticcast. So Staticcast is a nice one because it makes clear this is a compile time cast. It's something we run at compile time, or we consider and do it when the thing has been compiled, not at run time. So it makes clear here where the cost of doing this actually arises. So it's quite a fast way of converting data from one type to another. And it's quite nice how it manages it. So it used to perform type conversions that are legally supported within C++. So this includes built-in conversions between primitive data types, so a bool to an int to a float, any of the normal conversions we can do. And it also extends to any classes that we define, and there's some rules around how this works. And we've got an example here. We've got two classes, class A and class B. So class A is defined to have one no argument constructor just for A itself. In class B, we've got a couple of constructors. We've got the default no argument constructor, and we've got parameterized constructor B that can enable a B instance to be constructed using an A instance. So we've got line 5, you can have a look at how that works. I'm going to assume just under those we have two methods, foo A and foo B. Foo A accepts an instance of type A, foo B accepts an instance of type B. So far so good. So let's have a look then at the 8 lines of code down at the bottom. And lines 1 and 2 we're declaring an instance of A and B. So far so good. And line 4 we are going to foo A. So foo A accepts an instance of A, and we're trying to pass in a B. And the compiler will go, no, foo A accepts in an A, you're trying to give me a B, doesn't work. That'll be compilation error. Even in line 5, if you try to do a static cast and you said, okay, it takes in an A, take B, and turn it into an A, it also will fail. Now, what it will do in this case is it's going to try to go to the, well, we'll go to the A class, and it's going to say, right, I've got a B here, I need to turn a B into an A. Are there any constructors that are defined within the A class that would enable me to do this? It looks through them, there isn't. There's only the default no argument constructor. So Staticcast will say, well, I've tried, but I don't know how to convert a B into an A, so it fails. In line 7, we're going the other way around. So here we're calling foo B, and foo B accepts an instance of type B, but we only have an A, so we're using our static cast, and we're saying take this instance of A and turn it into a B. So whenever static class sees that, it'll go off to the B definition, it'll look through the constructors, and it'll say, is there any constructor that enables me to construct a B from an A instance? And there is. We've defined that constructor at line 5. So what happens there for that particular static cast is that we create a new B, we make use of the constructor where you pass in an A, and then when that class is constructed, it then gets passed into foo B. So that's an R value class. It's one that is a temporary, one that we don't get access to, but it is actually created. In line 8, it does exactly the same. So even if we don't explicitly indicate that we want to do a static cast, and we should use this here explicitly because it communicates to the reader, the other people who are looking at this, what it is we have done. So in line 8, it'll happen implicitly anyway. So we've got an A and B coming in, it'll try to find a way of doing that particular conversion. So static cast, nice thing, nice that it's done at compile time, it's a sensible set of rules around it. One thing to be cautious about there is that you can use static cast for doing up or down cast within a class hierarchy. So if you have different base class and more refined class within it, you can use that for casting up and down. But it is a compile time cast, it's not a runtime cast. So you need to be cautious in terms of how you do this. So if you're going from a specific instance to the more general instance, that's always safe to do. But if you're going from a pointer to something for the general one and you're trying to make it more specific, you need to be careful about that, because if at runtime you don't have this, then it will cause issues overall. So the thing that you're meant to use in terms of that particular form of casting is a dynamic cast. So Dynamiccast, the name sort of highlights it as something that is done at runtime. Now, being doing it at runtime means that, well, it's tested at runtime. There's a cost to it, so it's slower than a static cast, which is done at compile time. But the benefit of this is that if you're not certain that the instance you have is going to be of the particular type, there's a risk that it may not be, then you can use that dynamic cast to actually check to see, is it a safe cast to do. Now, if it's not, there's two different ways that this can be signified. We can see them here, so we'll look at the example. So at the top, we've got a class or base class. In line 2, we've got our drive class, which is a type of the base class. So in line 1, we're creating a new base class. And in line 2, we're doing a dynamic cast. We're saying here we've got a pointer to the base class, but we want to turn it into a pointer to our drive, to a more refined class. Now that may fail depending on what the base class actually is. In line 3, we check to see the pointer. Now, if it isn't equal to null, so it's not null, non-null pointer, it means it was successful. The dynamic cast was run, it checked, and indeed our base class was a type of the derived class that we indicated. If the dynamic cast looks at it and finds, no, okay, I've got an animal here, you've tried to cast it into a dog, it really was a cat, you'll get a null pointer back, and you can detect that and then take some other appropriate action. Line 6 to line 10 shows you the equivalent thing if you're dealing with references. So we've got our base reference, and we're trying to create in line 9 a derived reference. So we're doing our dynamic cast to a derived reference from the base type. So again, we can do that. If this doesn't work, because you cannot have a null reference, and a reference must always point to something. References are not allowed to be null. In this case, you can't check for a particular value. You go for the catch, so it throws an exception, a bad cast exception, and you can pick that up and then take some appropriate action based on it. So dynamic casting and static casting, they're nice pairings overall. The last type that we have is Reinterpretcast, which is basically old style C++ casting. So it can be used to perform casts that are otherwise not technically allowed. So pointer types can be cast to any other type of pointer. References to one object, you can turn them into references to another. Pointers can be cast to ints to pointers. Basically, it enables you to reinterpret bytes that you're pointing to as any other thing that you want to. It's fundamentally dangerous, and there probably is no good reason why you would need to make use of this. So kept in, you got old style C++ casting, I suppose backwards compatibility in terms of support in C++ 11. Shouldn't be doing that. Really use the other forms of casting. So we're going to finish up just by very briefly looking at the differences between classes and structs, or classes and structures. Now, we'll talk here about what the actual difference is between them in C++, and then a little bit more about how they're meant to be different. So the key difference between structures and classes in C++, particularly in C++, are that the methods and data are public by default within a structure, and they're private by default within a class. So in C++, there is very, very little difference between a struct and a class. They're more or less identical, just depends on the assumption of it being open and visible to everything or closed to everything. So you have a lot of freedom to use them interchangeably, but you shouldn't do that. Generally speaking, for structures, you should use them to hold data. If you have a clump of data that needs to be tied together, use a structure. If you find that you have a bunch of data that needs to be tied together, and alongside that there are a number of methods that need to be associated with that clump of data, that's a class. So it's useful to adhere to that. Classes bind data and functionality together. Structs just bind data together. And if you adhere to that, that'll sort of keep you straight and narrow in terms of how most people will look at or perceive or interpret a class or a struct. So takeaway in this, there is only one, well, I mean, you can do structs in this keyword. The only thing I want to mention here is about the casting is the main takeaway on this. So there are some nice aspects to how C++ 11 does it. There's some not so nice aspects, but it's useful then to take a step back and to think about what it is we are doing when we are casting one object into another and some of the processes that are associated with that.